Welcome back to Math Explore Infinity. I'm thrilled to dive into another fascinating mathematical concept that might seem a bit abstract at first, right? But fear not. I will try my best to motivate it, right, in a way that is understandable, even if you are not a mathematician. So today we are actually exploring the intriguing world of the open mapping and closed graph theorem, right? So um, just imagine, right? Imagine you have a map of a city, right? Like the kind you might use when you are driving around, right? I don't have a car, right? I hope you do, right? So this map shows actually all the streets, buildings, and landmarks, right? Now, let's say you want to represent this map digitally, right? Like on a computer screen. So the open mapping theorem is kind of like a hole that says if you have a really fancy map and you want to show it on a computer screen, you can do it in a way that preserves some important things about the map. I mean, in more technical terms, actually, I mean, it's about transforming one space, right, into another in a way that respect the structure of the spaces. So imagine, I mean, the city map being transformed into a digital version, right? While still maintaining the relationships between streets and say, landmarks, for instance. So similarly, the theorem actually deals with transforming certain mathematical spaces while preserving the structure of those spaces. So, for example, think of the map, right, as representing a mathematical space, right, where um, you have points and some sort of connections or relationship between them. So the open mapping theorem says that if you are able to take these points, right, and connections and maps, and I mean, if you're able to take these points and connections, right, and map them onto another mathematical space, then as long as this mapping is, I mean, open, I will say open here, right, which is, I mean, which hopefully means it doesn't overly distort things, right? You can say, I mean, you can see openness here as something that's, I mean, that behaves well actually somehow. So the connections and relationships between the points are still preserved. So the open mapping theorem is a bit like a guarantee that when you are converting a representation of a space into another, as long as you do it in a certain way, um, you are not going to lose important information about how things are connected. So let's state the theorem, right, itself. So theorem 1, so call it theorem 2.6, like in continuation with our lecture series. So theorem 2.6. Call it, so the open, start with the open. It doesn't look nice. The open mapping theorem. So let E and F be two Banach spaces. Right? And let G be a linear bounded operator, right, from E to F, that is surjective. Right? Surjectivity is very crucial here, so I'm going to highlight that. Then the open mapping theorem states that there exists a constant there exists a constant C positive strictly greater than 0 such that we call it 7 such that let's keep the same color. The ball, the ball in F, right, centered at 0 and radius C is actually contained into the image of the unit ball in E. Okay, so well, let's take a remark just for our understanding of the theorem, right? So property 7 that you see written here has another interpretation, right? Or implies something. Property 7. Property 7 implies that the image of any open set in E is an open set. It's an open set in F. Okay, so basically the open mapping theorem says that if you have two Banach spaces and a linear bounded operator between those Banach spaces that is surjective, then the image of an open set in E through that linear bounded operator it's actually it's still open in F. So let's have a very quick proof. Very quick proof. So let's prove a statement. So indeed, and we put it maybe in a bracket. So indeed, let's assume. So let's assume, say U, right, is open in E. Is open in E, right, and let's prove that. T of U, the image of U via T is actually is open in F. Okay, so let say y0 might belong to TU. We aim at showing that we can find say an epsilon ball around y0 that is contained into T of U. So let y0 in TU, that means y0 is actually tx0, right? If for some x0 belonging to U, right? But U is open, right? U open implies that there is an R ball centered at x0 that is contained to U, right? So this means that take a step. This means say y0, maybe it goes slowly, right? So this means T of x0 plus rather right, C R times T of the unit ball in E is contained into TU. Now using property 7, right? Using property 7, we get that y0, right, plus the ball in F, right, and total 0, and we just C, and now just RC, there was an R in front of T, so this is contained into C of U. So this means the ball in F, right, y0, I mean, don't forget that y0 is, I mean, it's actually T of x0, so don't get confused. So this is contained into Tu, once Tu is open. So this concludes this short proof. Okay, so now before proving the open mapping theorem, let's have a look first at some consequences of the open mapping theorem. So corollary 2.7. So let E and F be two Banach spaces, and let T be a linear bounded operator from E to F, right? That is, let me use another color, that is bijective. Then the inverse of T is a linear bounded operator, then T minus 1 is a linear bounded operator from F to E. Okay, we'll have a look at the proof. So let me put, how will I put it, and put it that right, yeah. So, and then I will just say linearity is okay, right? So that, I mean, you can check that, right? That C minus 1 is actually linear, so it's not actually a very big deal. So let's rather prove the continuity of T minus 1. Okay. Let me put another start. So just to be clear, the continuity. So this is what we are about to prove. Okay, so we go, I mean, we go kind of, I mean, we are going to start right away, right? So, because remember that, I mean, we have the assumption that T is a linear bounded operator that is bijective, so it is surjective. So we know that, I mean, by the open mapping theorem, that property 7 holds, right? So I'm just going to write, I mean, property 7, right? And the assumption that that T is injective, imply that, I mean, if X is in E, right, is chosen, so if X is an element of E is chosen such that the norm of Tx, right, in F strictly less than C, then the norm of X is necessarily strictly less than 1. Because, I mean, remember, let me put it, remember property 7 says, property 7 actually says that there is this C positive, right, such that the ball in F is contained into the image of the unit ball. So this property together with, let me drag it a bit to the right, to the left. So this property together with injectivity just implies what I just claim here. So if X is an element in E is chosen in such a way that the norm of Tx is strictly less than C, then you necessarily have this condition here. So again, if you have any problem or questions, so feel free to leave it in the comments. So so we have that. So then, sorry. So then by homogeneity, right? We have or we find that it's better. We find that the norm of X in E is actually less or equal to 1 over C times the norm of Tx in F in this for every X in E. Right? Well, to see the homogeneity thing, so put indeed put, of course you know that if X equals 0, there's probably there's nothing to show, so put Y equal to Cx over norm of Tx in F, right? Then you see that the norm of T of Ty in F is actually strictly less than C, right? Which implies, by what we stated above, that the norm of Y is strictly less than 1. And then if you actually kind of expand norm of Y strictly less than 1, you get exactly this relation here. So and then we are done, right? Because this means the norm of Tx in F is actually greater equal than C times the norm of X in E. So once this is continuous. Okay, well, we are done with the first proof. So another consequence of the open mapping theorem is the following, right? Which is actually, some of you are probably familiar with that, right? Corollary 2.8. So let E and no, not we don't need two spaces, only one is enough. So let E be a vector space, right? And though with two norms, right? With two norms, say norm 1 and norm 2. So assume that E is a Banach space. Banach space for both norms. Right? It's actually important to say that it's a Banach space for both norms, because we know that a space can be a Banach. Can have a Banach space for a particular norm and not being a Banach space for another norm. So assume that E is a Banach space for both norms. Okay, and that there exists a constant C. Let's write well, let's say C positive, right? Capital C positive, such that the norm of X, the two norm of X, right, is also equal than C, which is capital C times the norm of X, norm 1. Then the two norms are equivalent. So what does it mean? So this means there exists small c positive, right, such that norm 1 of X is also equal than C, norm 2 of X for X in E. Okay, well, the proof is kind of a direct application of corollary 2.7. So we're not going to write the proof, just the outline. It's actually very easy. There's nothing difficult. So you say apply corollary 2.7, right? With now we need to define the spaces, right? With E, looks like a tautology, right? So if E equals to this space and F equals to the order norm, and then of course the linear bounded operator should be identity. C equals how would I write it? So the identity of the linear bounded operator. So with that you have the result. Okay, so now let's prove our main theorem, so the open mapping theorem, right? The proof is a bit lengthy, so that is why I decided to present first the consequences of the theorem before starting the proof, right? So proof of theorem 2.6, that was the open mapping theorem. Okay, so we split the argument into two steps, right? So we split the argument into two steps. So the first step, right, we show that step 1, and we are going to prove every step, of course. Step 1, assume T is a linear surjective operator from E onto F. Then our claim is that then there exists a constant C positive, right, such that we call it 8, right? So we can easily refer to that later on, such that the ball is actually contained into the closure of the image of the unit ball. Okay, so let's prove this first. Proof. I'm using different colors, so I mean it doesn't look messy. But okay, for the proof is a bit constructive. I consider the set xn being equal to n times the image of the unit ball, n times the image of the closure of the image of the unit ball through the operator T. So since T is surjective, since T is surjective, we have F being equal to the union of the xn, right? And greater equal than 1. Well, very quick proof of this statement. In fact, indeed, right, for every y in F, right, note that if y equal to 0, then there is nothing to show, right? So for every y in F, we may assume that y is different from 0. So there exists x belonging to E. This is definition of surjectivity, right? Such that y is equal to tx, right? But this is again equals to what? To norm of x. We use the linearity property of t. So this is norm of x times the image of x over norm of x. Of course, if you assume that y, I said y is different from 0, so that will necessarily implies that the x is also different from 0. Otherwise, we have you have t of 0 equals to 0, which is which relates to a contradiction. So for every y in F, we can always find an x in E such that y is equal to tx, right? And this can be rewritten as norm of x times t times the image of x over norm of x. Of course, x is different from 0, as I said. So this means we can always find n0 strictly positive, right? Such that y belong to n0 times the image of the unit ball. So this concludes, this kind of proof the statement that F is exactly the union of the xn. Now, since F is complete, right? F is of second category. So that means there is this an index n0, right? Such that xn0 is not nowhere dense. That means the interior of the closure is non-empty, right? So but xn0 is obviously closed, so this means the interior of xn0 is actually different from the empty set. So this means just replace xn0 by its definition. So this means the interior of the closure of this is different from the empty set. So let me drag it slightly down for clarity. So this means, right, that we can find there exists a y0 in F, right, such that y0 belong to the interior of the closure of T of the unit ball. So this means, by definition of, y0 being an interior point, there exists a C positive, right, such that and we call this 9, right, because we use it, such that the ball around y0 and radius say 4c, right, because it's actually contained into this closure. So in particular, y0 is an element of the closure, right? And by symmetry, we find that by symmetry we have call it 10 minus y0 is also an element of the closure. Okay, so if you add 9 and 10, then 9 and 10 actually 9 plus 10 implies that, let me just, okay, we see 9 and 10, so this implies that the ball around 0 of radius 4c is contained to this closure plus this closure. I'm trying to write every step. So, but on the other hand, since the closure of the image of the unit ball is actually convex, we have the summation of the two sets is equal to 2 times Good. And then, so, I mean, it follows quite easily now. So, it follows. So that means the ball around 0 and radius 2c is actually contained into the closure of this wall. Good. So we are done with the first step. So I'm not going to. Okay. In the second step, we assume that step 2 oops, good. So step 2, I mean, we assume T is now continuous, right? It's a linear bounded operator from E to F that satisfies it. Then we have (11), which is what we aim to prove. We have the ball totally contained into T of this ball. Okay, so this is, I mean, definitely, as you can see, this is the last step of the proof. So we prove this step 2. So proof. We prove 2, right? So as to make the difference. So let y belong to F be an element of F, right, with norm of y. So I think you should remind you that this is a ball in F. Of course, this is a ball in E, so don't need to write anything. So let y in F with norm of F in y with norm of y in F strictly less than C, right? So we want to show, let me just recall you, we want to show that, so we want to show that y, I mean, we want to, say you want to find, so you want to find x in the unit ball, right? So say x in E with norm of x in E is strictly less than 1, and y being equal to tx. Good. So, I mean, again, this proof is a bit technical, but not that technical afterwards. So, by 8, right? By 8, that is, let me remind you, 8, that is the ball just to see it's actually contained into the closure, the image of unit ball. So by 8, we know that for every, right, for every epsilon positive, right, there exists z in E with norm of z in E is simply less than 1 over 2, right? Simply less than 1 over 2, such that, such that the norm of y minus tz in F is actually strictly less than epsilon. I mean, this actually follows by um, by 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 8, because I mean you have y, which is actually the norm of y less than c, so y is actually in this ball but with radius c, so which is actually, that means y is actually contained into this space here, right, but with the radius 1/2. And now you just need, I mean, just being the closure means that, I mean, it's a point that approximate, I mean, you can find a sequence of points that approximate um, the point in questions. So, so by choosing, I mean, because epsilon is arbitrary, right? So by choosing epsilon to be c/2, so we find again, I mean, we find z1, right? Find z1 in E such that the norm of z1 in E is actually something less than 1/2, and the norm of y minus t z1, yes, simply less than c/2. Okay, so by the same construction, let me write it. So by the same construction, or proceeding iteratively, the same construction applied to y minus t z1, right? Instead of y, so you do the same thing, but instead of using y, you use, I mean y minus, I mean, the image of your constructed, of the, I mean, of your constructed point. So by the same construction applied to y minus t z1, right, with epsilon equal to c/4. So each time you actually halve, I mean, the radius. So we find some z2, right, in E, such that the norm of z2 is less than 1/4, right, and we'll write it here then, and the norm of y minus t z1 minus t z2 is less than c/4. So proceeding similarly by proceeding similarly, let's say by induction we obtain, so by induction we obtain the sequence say Zn, right, such that the norm of Z n in E, right, is less than 1/2 to the power n, and the norm of y minus t z1 plus z2 plus zn in F is less than c/2 to the power n. So it follows that follows that the sequence say x equals to summation of zk k moving from 1 to n. So you follow that the sequence of general term xn equals to the summation of the zk k moving from 1 to n. It's a Cauchy sequence. It's a Cauchy sequence. So I think this one you can easily prove, right? So I'm not going to do that, but if you have any problem, feel free to reach out to me. Like, so xn is a Cauchy sequence. So and then E is a Banach space, so there's a limit. So let xn converge to x, right? Then clearly, again, you can check that yourself, right? That the norm of x in E is equal less than 1, right? And y is equal to gx, right? Since well, you can check that. So I wanted to give you kind of sort of a ring, but I think that that's okay. Okay, so we're done. So we actually prove the open mapping theorem, right? So and now to conclude this chapter, we are going to this last part talk about the closed graph theorem. Theorem 2.9. The closed graph theorem. Okay, so let me probably, before stating the theorem, try to motivate it a bit, right? So consider you have a mathematical function, right, that connects input values to output values. Now imagine you are actually graphing this function, plotting the input values along the x-axis and the corresponding output values along the y-axis. So this graph, visually represent, how the function behaves. Now, the closed graph theorem is actually, is motivated by the desire to understand the relationship between the continuity of a function, right, and the shape of its graph. So continuity means that, small changes in the input lead to small changes in the output. And we want to explore, this continuity, how this continuity is actually reflected in the graph. So the key insight is that if the graph of a function is closed, right, meaning that it contains all its bounded points, right, it implies that the function is continuous. So of course we need linearity is important, right? We'll come back to that. So this is an important concept in mathematical analysis because it establishes the connection between the geometric properties of a graph and the analytical behavior of the function itself. So imagine, once again, imagine you have a function that is not continuous. So this would mean that at some point, right, the function either has a jump, right, or a break in its behavior. So where a small change in input result in I mean in say a very large change in output. So this behavior would manifest as gaps or abrupt changes in the graph of the function. Now, on the other hand, if a function is continuous, right, it means that the graph can be drawn without lifting your pencil. So the line you draw will smoothly connect the points without any gaps or changes, right? So this line connecting all, the line connecting all the points on the graph is what we mean by, a closed graph. So the closed graph theorem formalizes the idea that, if the graph of a function is closed, then the function is continuous. So it provides a sort of a mathematical tool for analyzing the continuity of function based on their graphical representation, so to speak. So in summary, right? In summary, the motivation behind the closed graph theorem lies in the desire to understand the relationship between the shape of a function's graph and its continuity. So by establishing that a closed graph, right, implies continuity. So the theorem actually gives us a way to link geometric properties with analytical properties, offering somehow a kind of, a deeper insight into the behavior of functions. So maybe let's stop and stop talking and make and try to, to get back into mathematics. So let E and F be two Banach spaces again. Be two Banach spaces. Right? Let T be a linear operator from E into F. Let me highlight linear because as I said, linearity is important, is crucial. So assume that the graph of T, right, that we will denote G of T, right, is closed. Is closed in the Cartesian product, the Cartesian product E times F. Then T is continuous. So before having a look at the proof, so let's take this remark. So the converse is obviously true, right? If you have a function that is continuous, then the graph is obviously closed. So the converse is obviously true. Write it in color. Since the graph of any continuous, right, be this linear or not, is closed. I mean, you can prove that if you want, right, as an exercise. Okay, so proof. Well, the proof is not complicated, right? So consider E the two norms, the two following norms, right? norm 1, right, which is defined as being, the graph norm for those who are familiar with the notion of graph, right? So then we consider the true norm that will be defined as being the norm of x in E only. So just for your recall, so this is graph norm. Okay, so under the assumption that the graph is closed, right? One can verify that E and O with the graph norm is a Banach space. It's a Banach space. Of course, I leave this to you, right? So on the other hand, E and O with its usual norm is a Banach space by assumption. Banach space, and we have the following relation. The norm 2 of x is always and always less or equal than the norm 1 of x and the graph norm of x, right, for every x in E. So it follows by corollary 2.8, I think. Followed by corollary 2.8 that norm 1 and norm 2 are actually equivalent. So thus, so that means there exists C positive, trying to get it right. There is a C positive, right, such that norm of x1 is less or equal than norm 2 of x for every x in E. So this means I'm just rewriting norm 1. So this implies norm of x in F is less or equal than C norm of x in E for every x in E. So once C is continuous, and we are done. Good. So maybe take this last remark, right? As I said, why is linearity important? So let's have a look at this remark. So linearity is crucial. So indeed, consider the following map. Right? Consider the operator defined from R to R, right, which which maps x to t of x, like just equal to say 0 if x is less or equal than 0, and 1 over x else. So the graph of t is equal to what? To input bracket like this, minus infinity. This will be minus infinity 0. I mean, this one you can check, but I mean, I think there is really nothing to check. It's rather straightforward. This is equal to this union with the set of x, y, right? Such that we write it down here, x is positive and y is equal to 1 over x. Okay, the graph is closed, obviously, right? Finite union of closed set. So this is closed, but see, it's not continuous. So let me highlight that. See, it's not continuous. Although, nope, this is not nice color. Good. So this means, as I said, that let me write it again. So this means the closed graph theorem aims to derive properties for a linear operator T, right, between Banach spaces to be bounded or continuous. Good. So with this we end this lecture. So thank you for joining. So we see each other in the next video.